Welcome to the course on power quality. We will discuss today this improved power quality converters. Out of that we will discuss AC to DC boost converters, coming to like a outline part of it, starting with the introduction, state of art on improved power quality converters. We will discuss about this improved power quality converters classification, then principal operation and control of improved power quality converters, then analysis and design of improved power quality converter, modeling, simulation and performance of improved power quality converter. We will have some numerical examples followed by summary and references like. So, first we would like to discuss objective about the requirement and applications of these improved power quality converters. Then we talk about configuration of improved power quality converters and control of improved quality converters, analysis design of improved power and method of modeling and control of improved power quality converters like. Well, conventional AC/DC converters have demerits of poor power quality in terms of injected current harmonics, which causes the voltage distortion at the point of common coupling where they are connected, also called poor power factor at the input AC main, and cause the slow varying ripple in the DC output at load end, and have a low efficiency and large size of AC and DC filters if you are using filters to get the right input and output power quality. So, the solution to these problems are improved power quality converters, which also known as switch mode rectifier, or also in short we call it switch mode SMR converters like. Coming to state of art, the improved quality converter technology is matured for AC/DC conversion with reduced harmonic currents, high power factor, low electromagnetic interference and radio frequency interference at input mains, and well regulated and good quality of DC output, and the rating their rating ranging from fraction of watt to several hundred kilowatt power rating. And the improved power quality converters classification, we classified into different category, and these are the typical classification with unidirectional, bidirectional power flow like boost converters, buck boost converter, multi-level converters. Of course, another classification can be based on supply like single phase and three phase. Typical, for example, here unidirectional boost converter is used for in switch mode power supply, low power adjustable speed drive in fan, air conditioner, welding machine, and other home appliances including washing machine, and even typically like your even the ceiling fans. So, plenty of the other category of improved power quality converters for high voltage and high power applications are like multi-level converters and multi-pulse converters like. So, coming to the classification of these improved power quality based on topology, you can classify boost converter, buck boost, multi-level, and based on unidirectional and bidirectional output voltage, and based on of course, the current and power flow. Well, another classification, we classify them on the basis of converters, whether you are using voltage source converters or current source converter, or you are using boost converter or using buck converters into that. And another classification is of course supply based like single phase and three phase converters. Another structure based configuration can be like a bridge based topology or semi bridgeless board topology or fully bridgeless topology. And of course, design and control based classification is whether these converters are designed for continuous conduction mode or discontinuous conduction mode or critical conduction mode. This is corresponding to energy storage device, which may be energy storing device, or you can call it energy transfer devices, maybe inductor or capacitor. So, these are the three modes of operation for these typically improved quality converter, especially for lower rating in single phase like. So, typically coming to like a first single phase boost converter, you can normally what we use the simple diode rectifier followed by an inductor and the switch and diode, and followed by the filter capacitor. And the very purpose of this is that we should get a regulated output DC voltage. It is a boost converter. So, you can have this output voltage always greater than the peak of input voltage, and then we want to have this current supply current sinusoidal in phase with the supply voltage. so that you get a power factor correction also with reducing harmonics, and of course, diode rectifier does not have any reactive power burden. So, for this I mean like this is quite popular converter which we call it boost converter, PFC boost converter, power factor correction corrected boost converter, extensively used in plenty of application, because the major advantage of such converters are that you get regulated voltage irrespective of varying voltage. I mean input voltage might vary, like in India we can have a 170 to 270 volt, but still you can maintain output voltage typically like a 400 volt or 380 to 400 volt. So, then the load part, I mean which load may be of different variety which we are discussing. It may be a adjustable speed drive of smaller rating, or it can be like a your lighting system, or it can be even a welding system. So, plenty of loads are there, or power supply, I mean where this used as a front end converter. So, you get a good quality of output DC voltage well regulated. Apart from that, you could get a good quality current in the input supply, and you can operate, I mean output voltage still can be regulated, even input voltage varies over a wide range. So, you might have a voltage power quality problem, but still the converter will give, I mean the load which are connected at the output of it is not supposed to be affected by such power quality problem which are really on the supply side like. So, of course, for this boost converter, I mean you will find lot of literature you will find on this boost converter, and now it is already appearing most of the even books also on power electronics, because they are very extensively used. And well, the basic control, 3 control which we talk about, it is first is the peak control. The concept of peak control, of course, what with this converter we like to control the output voltage across the load, which is a feedback here, and we have a reference voltage. So, we have a normally we call it error amplifier, but virtually it is a normally PI controller. It can be implemented in digital or analog way. You have plenty of chips for this PFC from most of the leading manufacturer, from the semiconductor manufacturer, whether it is a National Instruments or whether it is a your Textra instrument or typically analog devices. So, plenty of power factor correction chips are available for the control of them. So, output of this we consider the amplitude of supply current, we take the phase from here, I mean from sensing here, because these are the rectified voltage which have a of this shape. So, we take a shape from here, multiplied this with the output of controller, that is the virtually you can call it it's a current like amplitude, and this is the phase. So, we are getting here, and we are sensing the device current from here, that is the peak device current, and which give here, and after comparing this error and we compare with the external ramp, that is the carrier frequency corresponding to, and we give to this typically to this RS digital flip flop which give the getting signal to this device. So, this device can be of course for low power normally we take a MOSFET, and for little higher power maybe 2-3 kilowatt we go for some time even a IGBT. Of course, taking a MOSFET, the very purpose is that you can go quite high good switching frequency. People even work out this converter even up to 100 kilohertz. The advantage of going to be high switching frequency, that the size of the inductor can be reduced, and you can request power really the typically the voltage across the capacitor energy recover, it can be recovered very fast rate also, but size of the inductor reduces, which will reduce the size of your total converter also or so. So, well, this is the waveform how really peak current, once it touches the peak current, so you switch off the pulse, and that is we call it the peak current control. Like another control of this this peak current control, what are the advantage? We get a constant switching frequency, only the switch current must be sensed, and this can be accomplished by a current transformer or Hall effect current sensor, or thus avoiding the losses due to sensing resistor, or it can be sensed even sometime like by a terminal in the MOSFET which represent, because when MOSFET conduct it behave as a resistance. So, you can take a voltage drop of the MOSFET while it is conducting. So, that can also give you current sense flowing through that. So, you will be able to reduce the cost of it, and no need of current amplifier and its compensation, and possibility of a true switch current limiting. So, these are the benefit or advantage, but there are some disadvantage, presence of subharmonic oscillation at duty cycle greater than 50%. So, a compensation ramp is needed, and input current distortion which increases at high voltage and light load, and is worsened by the presence of compensation ramp, and control more sensitive to the commutation noises. Well, the another control for this boost converter, I mean PFC power factor corrected boost converter, typically shown here, we call it average current control. So, we control on the basis of average current, and the control loop in the same way, output voltage regulation, we take a feedback, we have a reference, we have like a PI error amplifier, maybe like a PID or PI controller, which give the amplitude of current, we take the phase from here, multiplied them, this gives a reference current which is flowing in the inductor, and we take a feedback current, that current here, and again we have a current amplifier. So, this can be again PI or PID controller, and then we compare with the sawtooth and give the gating signal. So, virtually here we are controlling the average current here like typically. So, with this also we get a of course, the power factor correction on the supply side and output voltage regulation also. This we call it average current control. Another the average current control have advantage that constant switching frequency and no need of compensation, and control is less sensitive to commutation noise due to the current filtering, and better input current waveform than the peak current control, since near the zero crossing of the line voltage the duty cycle is very close to 1. So, reducing the dead angle in the input current, but there are some disadvantage. The input inductor current must be sensed, a current amplifier is needed for its and its compensation. Network design must take into account the different converter operating point during the line cycle. The third control of it, why they are so controlled, because this circuit is very extensively used. So, we have a hysteresis control, concept of hysteresis, that the current should be maintained within the hysteresis like here. So, you have again here the feedback voltage, we have a reference voltage, again you have a voltage amplifier that give you amplitude of the typically inductor current. We get the phase of from this voltage, the phase of it multiplied, we give a reference inductor current, we sense the inductor current, and then we keep in hysteresis band by the two comparator, and then we give the gating signal to the switch. So, current is maintained within the this hysteresis band. So, we call it this is a hysteresis current control. The advantage, no need of compensation ramp, low distorted input current waveform, but disadvantage the variable switching frequency, and inductor current must be sensed, and control is sensitive to the commutation noise. So, another is the borderline control of this. Borderline control means we also call it critical conduction mode, this control, that every time the current touched just 0. So, neither we are going in discontinuous current mode, nor we are, so we are taking benefit in this case of both, I mean indirectly. So, here also we have again the feedback voltage and reference voltage there. So, we have error voltage error amplifier like a PI or PID controller. We take the phase from here, multiplied it, so we get the reference current, I mean like, and from reference current of course, we sense the typically the inductor current indirectly for zero crossing detection, and we take a switch current also and give the gating signal to this. So, that makes sure that to make sure that zero crossing of the, this give us the point at the zero crossing here. So, the benefit of this, that we take the benefit of discontinuous and discontinuous mode, and size of the inductor certainly is lower in case of bonding case like. So, advantage of this borderline control is that no need of compensation ramp and no need of current error amplifier. For controllers using switch current sensing, switch current limitations can be introduced, and disadvantage variable switching frequency and inductor voltage must be sensed in order to detect the zero crossing of the inductor current, and for controller in which the switch current is sensed, the control is sensitive to commutation noise. Well, the another control of it, the discontinuous current. This control is very interesting in a sense, I mean like you do not need the sensor on this side, only by design you are able to get inherent power factor correction. So, you are sensing the voltage, okay, and you have a reference voltage, and the output of this itself you compare with the sawtooth, and that gives the gating signal to the switch. So, no input voltage, no input current sensing is required, and the another major benefit, we get discontinuous current, your inductor size is also reduced. So, as you can see here, I mean the inductor current is discontinuous here, but because of this you get inherent power factor correction. So, sensors, you can call it current, couple of sensors are completely eliminated here, but of course, at the cost of, what is the disadvantage? The peak current is much higher, because this is the current which you will get getting average current, I mean like typically inductor, but the peak current will be even sometime more than double in this case, because you are missing some period here to make sure that. So, we make a design for, of course, in this case for boundary condition, and then we keep the select the inductor lower than that. It means the inductor size is reasonably reduced in this case. So, the benefit of this discontinuous conduction mode, the one benefit is you are able to reduce the size of the inductor, another is you are able to eliminate the sensor, but at the cost of your typically the current peak current increases substantially high. So, switch rating, diode rating, that also increases substantially, and moreover this current also flow through. If you are not putting a MI filter here, this current flow through diode also, so diode bridge also should be high frequency. Otherwise, what we can have here, we have a MI filter, so that diode bridge can be a power frequency diode like. Well, the advantage of this discontinuous current is constant switching frequency, no need of current sensing and simple control. The disadvantage higher device current stress than the borderline control and input current distortion with boost topology also. So, that is about the boost converter. Coming to like a supply based classification of improved power quality converters, it can be like a single phase or 3 phase, and we can have a unidirectional power flow or bidirectional power flow in single phase, as well as we can have in 3 phase also unidirectional power flow and bidirectional power flow. And coming to like a further of classification of single phase, we can have a unidirectional, bidirectional, and unidirectional we have a boost, buck boost and multi-level in single phase, and bidirectional of course we can have a boost, buck boost and multi-level. So, this is the classification that single phase improved power quality converter can be divided into 8 category. I mean, I can mention here the applications, we will discuss with the circuit also. Unidirectional are used in most of the applications where you require only unidirectional power flow. Typical example may be which we already talk about, like air conditioner, okay, refrigerators, washing machine, fan, ceiling fan, welding machine, all these are the unidirectional power flow. But the bidirectional power flow you can think about like a typically using in in online UPS, okay, or you might be using, or I mean line inductive UPS, or you might be using like a many applications of such where regeneration is there, I mean like a traction, okay. Even for very high rating we use this single phase bidirectional improved power quality boost converter like, and even sometime we use the multi-level also in that like. So, we will discuss that later. So, coming to single phase unidirectional boost improved power quality converters, this is the typical circuit, I mean which we are talking about the boost converter. So, single phase unidirectional boost converter, I mean this is what we have done after diode rectifier. We virtually included this boost converter, which gives the benefit with proper design and proper control, regulated DC output voltage, and we get the inherent power factor correction on the input supply, means supply current in phase with the voltage, and TID also reduced quite low, maybe less than 5%, so that it meets the standard. So, you get a quite good quality output voltage as well as you get a good quality input current in this converter. And of course, we discussed it already for control of it, I mean like, so you can operate in that. If you are designing in DCM, the benefit of course is you are able to reduce the size of the inductor like. Then another circuit is typically with the 2 devices unidirectional here, you can see here, this we also call it, you can call it like a, it is also power factor correction converter, boost converter, but you can call it is a bridgeless, okay. The bridgeless in the sense like positive half cycle, I mean this is working with the typically as a boost converter, okay. I mean you are switching here, so inductor will store the energy via this, okay, and when you really switch off this, the current will flow through this capacitor here and will back through this diode. In positive half cycle, negative half cycle, this will operate, this will short your inductor, okay, and once you open it, and then the typically the power flow current will be through this. So, it is also we call it like you are using a 2 boost converter, I mean here you are using 1 boost converter, here you are 2 using, you can call it, so diode rectifier virtually you are eliminated here, I mean up to some extent. So, we also call this as a bridgeless configuration. The benefit of this is that the one is the inductor is moved to AC side. So, design of inductor become quite simple because it is a AC inductor now, and the another benefit is the drop of one device here, because if current is flowing, it flows through 3 devices, here it is only flowing through 2 devices. So, you can call it losses is also, converter losses also reduced by approximately by 50%. So, that is another benefit. The third benefit, major benefit you go, that it can give a good quality up to even quite low voltage, I mean low input voltage also. So, those are the benefit, otherwise you can understand the disadvantage of that you are using 2 switching devices compared to 1 switching device here. So, this we call it like a bridgeless boost converter also, or with the 2 device single phase unidirectional boost converter. The third topology, of course, you can have a asymmetric configuration for typically for this same boost converter with the 2 devices only, and or you can have a, this is interesting topology which is reported in the literature for this boost converter, that we have a 2 cell single phase unidirectional boost converter. Out of the 2 cell you can see, we say 90% energy or power is at low frequency. So, we design one as a with the typically of low frequency, I mean like, and another with the high frequency to handle only 10% of power with that. So, but the high frequency one operate at high switching frequency, and virtually, or you can say low power means major amount of power which is processed in the typically of your this, you can call it like a typically high switching frequency. After this, why we have considered so many control and so much is reported for this, I mean improved power quality single phase unidirectional boost converter, because they are very extensively used and day by day their application are increasing. I mean whether it is a home appliances or whether it is a commercial office, whether you are using in typically when your air conditioning or your typically lighting system. So, I mean most of the applications it has a presence like, I mean also. So, the basic circuit coming to like a basic analysis and design of it. So, you have this your typically a diode rectifier followed by your boost converter and with capacitor. So, if you control properly, this is the supply voltage, your current will be this manner, and the rectified here you will get this voltage, I mean here this voltage, and the current which is flowing in the inductor will be of this shape, I mean like after the diode rectifier. So, well we can say what will be the virtually the you can call it the VD, the voltage output will be VD equal to VD and power will be VDID. I mean like you can say this diode typically here VD is here and diode current. So, that will be the power, and this ID which is flowing into diode, of course, it will be discontinuous, but it will have a load current plus capacitor current. So, I mean if you look into Kirchhoff's current law, this is the current sum of this current plus this current, and that is the relation here like, I mean. And now this diode current can be again written like a load plus you can call it capacitor current. Capacitor is supposed to take the all ripple, and here will be the lowest frequency ripple will be the second harmonic. So, that is the ripple capacitor ripple current which will be absorbed by capacitor, and this is the equivalent to load current, because that is average or DC current like. You can call it ID average will be equal to I load, and it will be VD IS divided by VD. I mean it is from power invariancy side, in the sense at unity power factor input power will be or VSIS, RMS voltage of input, RMS current of input, and divided by VD into ID will be the output power. So, from which we are getting the output average current, and which is will be equal to the load current like. And the capacitor current, which is the ripple current, will be second component here, which have a second harmonics here. And now, to find out the value of capacitor, we can say even though the analysis carried out by using the voltage across the capacitor to be ripple DC, the VD can be calculated, VDC ripple can be calculated from this ripple current 1 upon CD I this. So, it comes this, and the peak value of this will be corresponding to when it will be 1, and from this relation we can find out typically the value of the CD here equal to your ID, that is nothing but load current divided by your 2 omega into your VD ripple. So, even if depends your how much ripple you can permit in the output. So, virtually you can call it, it depends on your fundamental frequency, because it is supposed to absorb second harmonics into it like. So, that gives you the capacitor design, because you know the virtually the output load current, you know the ripple how much you can permit, and you know switching your supply frequency. So, you can get the CD. So, CD you can call it the capacitor value does not depend on switching frequency, it depends on how much ripple you can allow and how much is the load current. If you allow the ripple more, capacitor value will be low value, and if load current is more, the capacitor will be more, because it is directly proportional to that like also. And coming to the value of inductor design, so we can call it the switching frequency for a one particular cycle, we can say can be written on the interval T on and T off, and we can say T on will be nothing but the current rising. So, LD into ID, I mean will be Vs, or you can call it LDI by dt will be equal to T if we take equal to Vs. From that we are getting for on period this cycle, so on period is here, and that can be written virtually, I mean from this on period this relation. And now for switching frequency we can write the relation similarly for typically for off period also, I mean like corresponding to off period, and from on and off we add both together and we will get the typically this relation. For off period you can call it like a I mean the difference across the inductor will be Vd minus Vs like, because Vd is more, so it will be Vd Vs. So, we can put the value of both and we will get the switching frequency 1 T on upon T off. So, this will be the relation, and we can take this ripple we can take here, frequency we can take here, and we can maximize this value. I mean we can scale normalized value of Vs nothing but this. So, we can take I ripple here, and this ripple we can take a derivative of this with respect to the Vs, and we can see at what value of your this Vd will be of your ripple current will be maximum. So, when we take a ripple current maximum, we get this relation Vs absolute should be equal to Vd by 2, that will be the maximum ripple current, and with this value we put it here, we will get this relation. So, you can call it like a maximum ripple current depends on DC link voltage, okay, and switching frequency, and from this relation we can find out, of course, taking the inductor here and ripple current here. So, the inductor depends certainly now on DC link voltage. Okay. So, if you have a higher the DC link voltage, you require higher the inductor, and if you have a higher switching frequency, inductor will reduce. If you allow higher ripple current, then also inductor will reduce. So, this equation give you virtually the inductance value LD equal to Vd upon I ripple into 4 into Fs. So, this inductor value can be calculated from that, like so. So, with this we are able to get a design of this converter like inductor and capacitor calculation. Capacitor we calculated from second harmonics frequency from this relation, and capacitor inductor we got from this. So, this gives the design of this boost converter to decide the value of inductor and capacitor like so. But you can clearly see that if switching frequency is higher, we will get certainly the inductor value lower, much lower here in that case. So, of course, we got also developed this converter, and these are the typical experimental results corresponding to 230 volt, where the design for 2 kilowatt power and the output voltage was 390 volt, and the TAD is only 4.9% or so, and you can see the power factor was unity here. So, it is not very difficult to develop this converter, like it was only for 2 converter, power factor unity and TAD less than 5%, 4.9% like also. Well, coming to like now analysis of single phase 2 switch boost converter. Like this is 2 switch boost converter, we discussed already that this was the virtually a bridgeless configuration. Positive half cycle, this work as a boost converter, negative half cycle, this work as a boost converter, and typically the benefit of this is that inductor is on AC side. The another benefit we discussed is that you are able to go quite fine control up to quite low level. And third is the losses is reduced by 50%, because now there are only 2 devices conducting at a time. Along with this diode is conducting, or along with this MOSFET, typically for sorting, you are having typically with this switch, you have a diode conduction also. So, that typically the benefit of it, and this also people have used it. So, typically taking example of your 1500 watt supply voltage of 120 60 hertz, output voltage of 200 volt, allowing output ripple 5%, switching frequency 36.5 kilowatt, desired current ripple is 10%. So, we can have a design example. The bulk output filter capacitor may be determined by setting the output ripple constraint by allowing 5% voltage ripple, and that is typically 5% of, if we put it, this is the voltage ripple here, and the ripple voltage will be like a percentage of this around 10 volt. From this we can find out now the value of capacitor from this relation. So, ID we can find out from the load current from given power, this is the load current. So, we can find out typically the capacitor value what is required for. So, this is the typical value, we select the little higher value as a standard value of 1300 microfarad. And coming to the calculation of this inductor, that is also we say key determined by 10% input current ripple. So, we can find out the current ripple how much will be there 10%, and from this inductor for that particular switching frequency we can look into, and we get correspond to that typically XL equal to from this relation, and L we can find out like a point you can call it 419 millihenry. So, you can find out like typically your switching frequency is quite high 36.5 kilohertz. So, the inductor value is quite high, even a less than half millihenry, only 0.419 millihenry, or you can call it 419 microhenry. So, we can select of course little higher value, that is 560 microhenry inductor in that case available little standard value like. So, coming to like these were the unidirectional of 2 kind, we give an example as well as the design concept. Now, coming to the we will consider some more example later, and now coming to single phase bidirectional boost converter. This is typically first circuit of boost converter with the 2 devices and 2 midpoint capacitor with the output. It can, what is the benefit of it? You can have a bidirectional power flow. You can feed the power from this side to this side or this side to this side. But the disadvantage with this, the entire current have to flow through this capacitor. So, size of the capacitor will be large also, and the output voltage have to be Compared to that, this is the circuit which very extensively used, bridge configuration, and of course, in this case also inductor is on AC side, and you have a capacitor here, and you can see this converter is quite versatile converter, that you can have a 4 quadrant operation of P and Q on supply side. You can generate by this reactive power also, you can generate even active power also you can feed, or you can take active power and it also can give you lagging reactive power, or you can operate at unity power factor also, which is normally required for. So, that is considered quite good, and it is used very extensively for many applications, like we are using like a solar grid interface. So, this side may be the solar system with the MPPT, and you can push the power to the grid also. So, in such many applications, I mean this very extensively used also, or may be typically used for even a traction purpose. Of course, not exactly in the same, but the concept is same, bidirectional single phase, I mean used in traction, because traction or metro you have a regeneration. I mean like, so even metro, because all are operated with single phase supply, either metros or the your traction, I mean railway. So, you can have a during regeneration power back, and some of the metros have a regeneration up to 40% like, or so more than that. So, you have to put a converter in a way that it can feed the power, not only taking the power to this side, it can feed to the grid also like also. Or you can extend for reducing the, because in single phase you have ripple on DC link to reduce the ripple. This is another configuration, that one more lag, and these are taken for reducing the ripple there by third lag. Or you can have another method for reducing the ripple. So, plenty of circuit I mean there, but this is we consider the, you can call it the another benefit of single phase bridge converter, that is this bridge you can operate with the unipolar switching. And the benefit of unipolar switching is that you are switching the devices at some particular frequency like 10 kilohertz, but the ripple in the inductor will be of 20 kilohertz. Or you can say you can reduce the switching losses to approximately half in this bridge configuration like also. So, coming to the interesting part of design of it, we can say here, I mean you have a here the converter fundamental voltage, this is the relation for fundamental voltage, you have a supply fundamental voltage. We do not expect any harmonics in supply voltage, but we have a here harmonics, that is why we are saying this is a fundamental voltage, and this is the inductor drop voltage, and the inductor drop will be corresponding to your VL equal to Ls dis upon dt, and assuming the Vs to be sinusoidal fundamental frequency component of converter, and Is can be expressed as a phasor like a V converter 1 fundamental and Is 1 respectively. So, choosing Vs as a arbiter, so we will less convert here, only fundamental should be there. And what is the inductor voltage drop? That is j omega Ls corresponding to fundamental frequency of supply into Is1. So, this is the inductor voltage drop, I mean which will be of course at 90 degree corresponding to the current, and the phasor of voltage we can take at 0 angle, the supply voltage with the frequency of omega. And now you can say these are the phasor corresponding to, I mean like a different operating condition. So, if you are having a let us say power flow as a rectifier, it is working rectifier means AC to DC converter, your supply voltage and supply current in phase, and for this condition you have a typically, you can call it the, this is the voltage of the converter, fundamental voltage of the converter, and then you have the inductor, that will become virtually your supply voltage. Or you can have a typically the phasor corresponding to when current is out of the phase, it means you are feeding the power to the grid. Okay. So, voltage here, current is out of phase means power is the minus, and then in this case also you are having a drop virtually which is perpendicular to it, it will be just this, and then this will be the Vc. So, you can call it like here how we really discriminate between these two, rectification and inversion. This we consider symmetrically to like a synchronous motor. Synchronous motor delta is always negative, and this is the induced EMF corresponding to synchronous motor. This is the synchronous generator where the induced EMF is always leading with that. So, with that analogy of your synchronous generator, you will be able to probably remember very well, and both are operating at unity power factor. If you want only to work as a condenser, you can have to show that this current active power will not be there, only reactive power will be there, and you can have a current at leading, and you can say Vs is there, but you will be adding the inductor voltage also in the same supply phase. Similarly, you can subtract also in that, and this will be your corresponding to your inductive phase. So, it can work as a pure inductor, it can work as a pure capacitor, and in between you want to operate it as a here. When it is operating, let us say as a rectifier, you can generate the leading reactive power, and when you are operating it, let us say feeding power to the grid, you can still then you can generate even the lagging reactive power. So, it can generate the, you can call it like a leading or lagging reactive power, or you can operate at unity power factor, and apart from that it can have a bidirectional power flow to work as a rectifier conversion from AC to DC, or you can convert DC to AC back like on so on. So, with this we can have a expression of active power Vs Is1 cos theta, and that will be Vs square Ls V con 1 sin 1 and Vs. This is the equation you could have dealt with very well in the typically in the power system, I mean like typically, and then the reactive power will be your by this relation in this case. But you can understand, making a operation with reactive power 0, it means you should have this value 1, and it is not very difficult because you have seen converter voltage slightly higher. So, this V converter cos phi, your converter voltage is higher, so this can be made exactly equal. So, this can be 1 and then you will have a reactive power 0, you can operate very well with no problem. I mean like, of course, the delta will be decided by power flow, because we consider that these two voltage will be very close to each other. So, this will cancel out. So, it will become Vs into V converter divided by x into sin delta. That is the typically power equation in power flow in your power system. So, same equation is taken here also, typically like a similar to like a with lossless, you can call it like kind of synchronous motor, like which is taking power from the grid and feeding to the mechanical side. So, exactly same, and you can have a power factor unity also there. So, that is the basic concept here, or otherwise you can have this typically delta 0, then active power will be 0, and from this I mean relative value by converter varying the converter voltage, you can control the reactive power whether it is positive or negative. Positive in the sense that you can have this term more than 1, that will be the positive negative reactive power, and if you have this voltage more, that is means your capacitive nature, and if this voltage is less, so this is less than 1, so you will have a reactive or inductive reactive power, lagging reactive power. So, you can generate all, or you can maintain this 0 and you can have a active power flow, and depending upon the delta, if delta is let us say or negative, it will take the power from the grid, feed to the DC side, and if delta is positive, then feed the power from DC side. Provided on DC side you have a source like which I have given example like in solar power generation, you can feed the power from the DC side and put to the grid like also. But you will be able to maintain unity power factor on supply side without any problem. I mean because of the high frequency switching, harmonics can be reduced to less than 5%, and of course, reactive power burden also can be reduced to 0 with the unity power factor operation. And you can call it fundamental current is typically the difference of these from inductor relation, and the converter voltage can be I mean always Vs square plus your reactance drop square under root of that, that will be fundamental converter voltage. So, that explains that always the converter voltage is always higher I mean than the source voltage, but not much difference because this term will not be very high I mean like, and moreover it is at quadrature. So, it will not change the converter voltage to different from that. So, now coming to like other topology of single phase boost AC/DC converter with high frequency transformer isolation. They are very extensively used in many applications like in switch mode power supply. We will talk about application also. I mean like, so boost AC/DC converter with isolation can be like a single phase improved power quality, AC/DC converter with the high frequency transformer isolation are known as input current shaper, high power factor single phase converters, power factor correction converters, and universal input single phase PFC isolated converter. And if you talk about classification from with high frequency isolation, you can have buck, you can have a boost, or you can have buck boost. So, we will talk about boost here, like you can use either for forward or push pull configuration, half bridge configuration or bridge configuration. And if you feed by current fed, they will work as a boost, but if you feed directly with voltage fed, then they will work as a buck converter, same topology with a slight difference like. And of course, buck boost are just typically flyback, Kirk and Sepik zeta converter, which can have a buck and boost operation for output voltage. I mean you can have a, so these names are how they are converting from AC to DC. If boost means you are boosting the voltage from input to output, okay, normally used for getting a constant output voltage with even input voltage vary. Otherwise also input voltage because of AC it will be varying over a wide range, and buck converter that output voltage you are reducing also. So, coming to like a single phase boost isolated forward converter. So, this is virtually our, you can call it after diode rectifier. This is our forward converter, and what we are putting in forward converter, we are putting only the inductor at the input, okay, and this inductor allow us virtually I mean the boosting of it, because when you close the switch energy is stored, and when you open the switch this energy will go through typically here. So, it will work as a forward boost converter current multiplier approach in the sense we are sensing the voltage and input current as we have discussed in the PFC. You have to sense the voltage and current, so output voltage regulation is there. We have a reference voltage and we have a feedback voltage and we have voltage controller. Output of that we will give reference current generator, for which we are taking shape form here, and then we are having a sensing the current form here, and from this we are giving switching to it. So, this is called current multiplier amplifier, but if you are designing this in DCM forward converter, virtually maybe this inductor you are designing in DCM or the transformer you are designing in DCM, then you know to sense this voltage and current, only output voltage regulation you can operate in discontinuous mode of operation like. And so, this is like a push pull converter, you can just see boost push pull converter. This is a EMI filter capacitor you have here. So, what we are doing here first, for boosting purpose we are switching on both. So, there will not be any voltage here, this inductor will store the energy, and when you want to transfer the energy you have to switch off one and switch on another, then energy will be transferred. In another half cycle of on the next cycle you will do the reverse like. And here also of course with the current you have a reference voltage, you have feedback voltage, you have voltage controller, you are sensing the voltage and giving, and the amplitude is from here, phase from here, you are getting this inductor current typically sense, and you are getting signal to this and this according to the whether both signal to the both or either to one or this one, that is the mode of operation with this your push pull converter. Similarly, for the half bridge, we can switch on both the devices which store the energy in the inductor, and when you can switch off one, the energy get transferred to the secondary side. So, here also we have a reference voltage controller, we have a shape form here, we get a reference current, we sense the current and we give the gating signal either to both or one in turns either upper and lower one. So, that is like typically half bridge, and we come to bridge. This is used normally for high power rating. So, here we can switch on either one leg or both legs simultaneously when we store the energy, and when we want to transfer. So, we can switch on diagonally this on this, so that transformer action is there and we can operate in the same manner. So, we have a sense voltage, reference voltage, voltage controller, amplitude, we take the phase form here and then we sense this and put a signal corresponding to either all 4 devices or we give to a pair of the devices like that. Really give us typically the power factor correction in this you can call it boost PFC circuit. So, this inductor virtually you can call it, we are making this converter current fed like also. Well, coming to after design and simulation, this is virtually you can call it like a forward topology. You can get the current very close to sine wave with the 2.8% TAD, and for push pull this is the typical current, the 4% TAD, and then half bridge you are getting 4.68 and full bridge you are getting 4.68. So, you are able to get with the good power factor correction sine wave for all these topology like and this is typically forward pushed with the DCM. If you are operating in discontinuous mode, of course, TAD slightly increases and here also slightly increases, but many applications for low power it is permitted even to go up to 17 to 18%. So, even it is less than 8% or so. So, this is for push pull, this is for half bridge again less than 8% and this is for full bridge. So, you can operate either in CCM or DCM by control, because DCM is a very simplified control, you can call it like up to some extent. And this is the dynamic performance of, you can call it push pull one in CCM, and you can say here load you are increasing and decreasing, and you can say how the supply current remain in phase with the supply voltage, DC link voltage remain regulated, input current are increasing because output power is increased because of increased load on the DC. But power factor is maintained, current is harmonics also reduced quite low, and this is the case corresponding to DCM of this. Discontinuous you are designing. So, here also you can see the current is increasing when increase the load, decrease the load. So, this is the dynamic performance of this like in DCM, and this is for typically in case of push pull with the CCM. Like you can say load increase, decrease and current increase or decrease, but remain in phase and remain close to sinusoidal also. So, coming to with this, we can talk the applications where it is used like a DC supply, telecommunication supply, improve power quality, power factor, ballast like lighting system, power supply for equipment like computer, medical equipment, printer, scanners, and drive applications for power factor improvement AC side, electric welding, high frequency welding virtually, and lighting such as CFL, LED lighting, all application we use these PFC power factor correction converter. Some cases we use of course isolated, some cases we use non-isolated like computer supply we use the isolated one also. So, this is the power supply equipment. You can think about where we are using this boost converter, and of course, with the transformer isolation you have a transformer. So, a lot of applications are coming, like including typically toys, games, all those where we are using this for power factor correction converter. This they use virtually DC supply, all that. So, you need the isolation, you need the virtually what the transformer action in these give. The very one purpose is isolation, another is sometimes you need the multiple DC supply, that is the second one, and the third one the benefit is you can scale the voltage like and sometimes you have to design the transformer with your quite discontinuous mode with magnetizing current itself, magnetizing inductance in discontinuous mode. So, this is something half bridge multi resonant switch mode power supply for power your PFC power factor application circuit, and which are used in DC supply like 36 watt switching mode power supply for SMPS adapter or 5 watt adapter, or your switch mode power supply for industrial switch mode power supply, or DIN rail mouse mountable DC supply, like, or telecommunication power supply which are used in telecommunication, and improve power factor ballast for LED, like, or your fixer of LED, where we need power factor always more than 0.9 or so, closer to 1, or you have a welding. I told you high frequency arc welding, or you have a electric. So, welding size get reduced because you are using high frequency transformer, but you need the power factor correction at the input to where these are used, or your lighting system like your CFL or kind of this. Like, of course, we are going now LED. It used extensively in compact fluorescent lamp also. So, now coming to like analysis, design and simulation of performance of PFC power factor correction bridgeless boost converter, and this is typically the bridgeless boost converter. You can clearly see here, like here we have eliminated the bridge. So, one positive half cycle, one boost converter work, in another negative half cycle another converter work, like so that is we call it power factor connection bridgeless boost converter configuration 1. You have another configuration also, typically operational of this, you can call it in positive half cycle, one positive half cycle as is shown the dark, that is for positive half cycle, and this is for negative half cycle, it operates also. And if you are designing a DCM, these inductor currents should be discontinuous, like which we already discussed earlier, like, and you can design this converter. This is the input voltage, this is the typically output voltage, and you can design the input for this CCM or DCM, and this is the output capacitor with the corresponding to second harmony, as we discussed already in boost converter, same way, like. And this is the another version of PFC power factor correction bridgeless boost converter. So, of course, you have to use the two devices, and this is the circuit for positive half cycle and then negative half cycle. But you can understand in some application we require two equal voltage. Of course, it is own load here, but sometimes you require two equal voltage with power factor correction, like a switch mode, your switch reluctance motor drive of 4 phase, you require midpoint. So, that can give you midpoint also for some applications like or so on. Can we stop here?